Okay, welcome back. Next up is going to be control plane policing. Now, before we go to speaking about control plane policing, if we pick up a router, so let's draw in here a router. We split this into two. Now, in the upper portion, which is in here, we have the routers, let's say the routers interfaces. So it doesn't matter if those interfaces are physical or logical, like a GRV tunnel or a gigabit interface. It's interfaces. And on the bottom side, we're gonna have the CPU of the router. So now what happens is that as traffic goes, let's say that this router router X has only telnet and SNMP configured as control plane or management plane protocols, that router in there. So the router only is aware about telnet, accepts some telnet traffic from specific sources and SNMP from specific SNMP servers. Now the problem is that an incoming, let's say SSH traffic or an incoming HTTPS traffic, both of them, if the router receives SSH or HTTPS traffic destined to itself, the interfaces are not aware, like, does the router allow that traffic or not. So what that means is that that traffic has to actually hit the CPU, both HTTPS and SSH. Both of them have to hit the CPU. And then the router is going to know, okay, so I got an inbound SSH session from whatever, or HTTPS session from whatever, but because I'm not configured for those services, either I'm not running those services, like services are disabled, or I'm configured for those services but not from those specific sources. So in both of those two use cases, that traffic still is going to hit the CPU, because only the CPU, the router, can say, okay, I got this packet, let me process it, let me see what is this packet about, and then I'm gonna say, okay, I'm gonna drop it because I'm not running those services, or I'm not allowing those services from those specific sources. So that is a problem, because somebody could, send a lot of those packets to the router and overwhelm the CPU of the router to begin with. That's one main problem to begin with. And then secondly, we have pretty much two type of attacks we need to protect against from a router's or a switch or any kind of device point of view. So denial of service attacks, which are going to be targeting the router's CPU, which is going to be incoming traffic to the router. So in that case, the router is the victim. Like as I stated, imagine that a router receives a huge amount of SSH packets or telnet packets, or doesn't matter, some kind of packets destined to the router's control plane, which is going to hit the router's CPU. And if the CPU becomes too busy, that's why it's called a denial of service. If the CPU is too busy to drop those packets, either because it doesn't run those services, or because it runs those services but it doesn't, let's say, accept that traffic from those sources, traffic still hits the router CPU, which means that if somebody sends enough packets at a fast rate, it's going to overwhelm the router CPU. If the router CPU goes to 80-90% or even more than that, that means that the router doesn't have enough time left, doesn't have enough resources left to take care of the actual control plane packets which allow the router to function, which allows data plane to work. Because if the router is too busy, handling SSH packets or HTTPS packets, which he doesn't actually accept in the end, he may not have enough CPU resources to deal with the OSPF packets or the BGP packets or with the R packets, which means because routing protocol is not going to work or ARP is not going to work, it means that in the end the router becomes isolated and data plan will not work as well. And the second type of attack is reconnaissance attacks, which is outgoing traffic from the router. So this is actually traffic initiated sourced by the router, which means router is the attacker. Now, one such use case, for example, is the following. Imagine that we have somebody, an attacker. Doesn't matter if it's from the inside network or from the internet. And what the attacker does, it sends, let's say, telnet sessions. It sends any kind of packet, like a telnet packet, which is sourced from the attacker, clearly. And it's destined to, let's say, an IP address which is not routable, so it's not destined to the router. Let's say destination is going to be 10.999. So this IP packet reaches router 3. It's not destined to router 3. Router 3 says show IP route that destination, and because router 3 doesn't have a route for that destination, what is the router going to do? So like, what does a network device, of course it depends on the type of network device, so for that reason let's take a router example. What does a router do when it receives a packet and destination is not routable? What does it do? So I'm a router, I receive a packet destined to 10.999, I accept it, I say show IP route, it's not destined to me, I don't have a route for the destination, so what do? So I drop the packet, correct, but what happens also next? So except dropping the packet, the router is going to send back to the source. It's going to send an ICMP destination unreachable type of message with a source of the router 3, destination of the attacker. Because we know that ICMP, it's a troubleshooting protocol, to call it that way, right? ICMP for IPv4, not for IPv6, right? So Matthew says route unreachable, it's ICMP destination unreachable, right? So router says, okay, it has to send a message back to the source saying, I cannot take you there, that destination unreachable, because I don't know how to route to that destination you're actually telling me to route to, correct? So because this is a packet sourced from the router, it means it's going to be a process switched packet. The router generates that packet, so it's going to be a control plane packet. So as a result of the router receiving, technically speaking, a data plane packet, which the router should route, but because the router didn't have a route to begin with, it's going to send back a, sorry, I cannot take you there, and ICMP destination unreachable. But that packet is going to be process switched by the router. So you can imagine that likewise an attacker could send a lot of such packets at a very fast rate, which is going to make the router too busy to send, tens, hundreds or thousands of unreachable messages, because that's what the router does. And those messages are going to again consume the router CPU, which may again make the router to go 90% CPU overload, which at that point the router is clearly unstable. When the router hits 80-90% CPU, you can expect unexpected behaviors. So again, the router may in the end, because it's too busy to handle those ICMP packets, then in the end the router may not have enough resources to process my EIGRP packets. Which means ASA3 is going to drop the IGRP adjacency with router 3 or BGP, whatever the IGP is, or BGP in there. Which means if routing protocol goes down, then this router becomes isolated. So data plane is down. Because if this router loses the routing information, data plane, control plane is down, data plane is down, and of course it's a lot of other, it's also the domino effect, which is even more, let's say, it's even more dangerous. So we don't want this to happen. Also, imagine that the attacker can actually spoof. So the attacker can send a packet with a spoofed source, which can actually be the source of, let's say, server ASA3. So if the attacker sends the packet sourced actually from one of the IP addresses of ASA3, it means that when the router generates that ICMP unreachable, it's going to send that ICMP unreachable to ASA3. It's going to send an ICMP reachable, destination unreachable, source router 3, destination ASA3. So it even consumes, at that point, this is even a better attack. Because with this kind of attack, the attacker can actually overwhelm the CPU of both router 3 and ASA3 at the same time. So for this reason, we want something, a feature that we can put on a router to limit both incoming, inbound control plane traffic. So like nobody can actually send me too many, like let's say control plane packets which I cannot process switch fast enough, and I'm gonna get high CPU. And also I want to configure the router to control how many outbound control plane packets can the router send in there, because in that case with the telnet packet which was destined to an unreachable destination, I would want the router to limit how many, for example, ICMP destination unreachable packets can I send outbound, how many of them can leave the router again. So we need a way to control both inbound and outbound control plane traffic to protect the router's CPU in there. So with Cisco we have two options for that. We have what is called control plane policing, which is also known as COPP, or control plane protection, which is known as CPPR. Now again, once we're going to speak about each of those two features independently, again the name of the feature is going to make sense. It's going to tell you exactly what it does. So once we define what they do, you're going to better understand, oh, so that name tells me exactly what's about. So pay attention also to the naming convention of any feature in there. It's not picked up, you know, just randomly. Also, you might think that this feature is heavily implemented because clearly the last thing you would want is that any of your network devices to be under the denial of service attack and to go high CPU. Actually, this feature is not that widely deployed because it requires testing and a network which does not grow in terms of control plane processing requirements. And for networks, so networks that you just make them run and they are stable, you don't add any additional control plane processing. Like for example, that's a network where you have a router which has 10 AIGRP neighbors and that's it. Tomorrow is going to have still 10 AIGRP neighbors. 2 years later, still 10 AIGRP neighbors. Because for networks where the control plane processing requirements are changing, it means that this capability requires constant adjusting. Because as I stated, how this works, what you're gonna do is you go on the router, you know what type of control plane traffic that router needs, like ARP and EIGRP, let's say. Because if your router runs only EIGRP to build the routing protocol information, and of course ARP for MAC to IP to MAC resolution, and you don't run IPv6, it means that router needs in a control plane should receive only ARP and EIGRP traffic. So then you're going to configure control plane policing to, as you're going to see, to secure and control how much traffic can you send and receive for those protocols, and all other traffic is going to be dropped in there. which means if the network changes, which means if the router ends up having not 10 neighbors, EIGRP neighbors, but 100, it means you have to adjust your configuration, because at that point the router cannot sustain 100 EIGRP neighbors, but only 10 of them. Now let's speak about control plane policing to begin with. So this was the first solution Cisco offered for its iOS code. And as the name states, control plane policing allows the router to police control plane traffic, both inbound and outbound. So what this means is that it acts like a virtual control plane interface. When you're going to do policing, it's like the router is going to have inside a virtual control plane interface, which is going to be controlling, is going to be policing how much traffic can the router receive control plane wise, and can initiate control plane wise for specific protocols. So it means this acts like a single queue, because you have only one virtual control plane interface which controls all inbound and outbound control plane traffic. And what we're going to do is a basic policing. Traffic exceeding the configured limit is going to be dropped before hitting the CPU, so it prevents CPU attacks. While traffic exceeding the configured limit is also dropped before leaving the router, prevents reconnaissance attacks. So to give you a visualization of this, what this means is that if you take that router again, we now divide the router into 3 sections. In here, at the bottom, we still have the router CPU. At the top, we still have the router's interfaces. But in here in the middle, we have that virtual control plane interface. Virtual control plane interface, which is going to limit what kind of traffic and how much of that traffic control plane wise can hit the router CPU. So it's going to be an inbound configuration. Likewise, it's going to control how much traffic and what kind of traffic control plane wise can leave from the router. Outbound policing. So inbound and outbound policing. Which what this means is that if you're, let's take the inbound option. If you, in your inbound policing option, you configure in here saying that a policy which states allow only EIGRP traffic. Allow only EIGRP traffic. But for example, 100 packets per second, not more than that. And drop all other traffic. Drop. Of course, you have to also allow ARP, right? So you allow EIGRP 100 packets per second, and you also have to allow ARP, whatever, let's say 50 packets per second. That's your inbound policing configuration, and you drop everything else. So else is going to be a drop. So this configuration, what this means is that if the router receives an incoming HTTP session destined to the router, it's going to match on my drop configuration, and it's going to be dropped instantly by my virtual control plane interface before reaching the router CPU. So that's what the advantage of this. And likewise for the allowed type of packets, like for EIGRP and ARP, if I receive inbound traffic EIGRP or ARP, whatever exceeds that value of 100 packets per second or 50 is likewise going to be dropped. So because I know that if the router receives, for example, more than 100 packets per second of type EIGRP or ARP, the CPU is going to blow away, and I don't want that, right? So this function behaves like an intermediate level between the router CPU and the interfaces, and controls how much traffic and what kind of traffic can reach the router CPU, and how much traffic and what kind of traffic can leave the router's CPU, which is going to be clearly for control plane and management plane traffic, because that's traffic destined to the router or initiated by the router.